Today we're beginning Chapter 5 for Pre-Calc. It's on analytic trigonometry. Our overview says in this chapter you will learn that trigonometry, with its many connections to triangles and circles, enables us to extend the problem-solving tools of geometry significantly. We hope in the process to give you an appreciation for the rich and intricate tapestry of interlocking patterns that can be woven from the 6 basic trig functions. So our first day here, we're going to look at the top 3, the fundamental identities. For the first part of this chapter. We will split it into 2 chapters, testing after the first 3 here. Fundamental identities, proving trigonometric identities, and sum and difference identities. And then in the second half of the chapter, we'll look at multiple angle identities and the law of sines and cosines. So for today, we are looking at identifying and working with trigonometric identities. We'll talk about the basic trigonometric identities, Pythagorean identities, cofunction identities, and even and odd identities. And we'll start simplifying some trigonometric expressions using those identities. And then tomorrow we'll tackle the third one there, solving trigonometric equations using the identities and properties of algebra. All right, so quick review. It says, for example, 0 here without having a unit circle in front of you. But I want you to take a second and think about the ordered pairs that are associated with pi over 6, pi over 4, and pi over 3. All right? For pi over 6, the ordered pair is the square root of 3 over 2 and 1/2. For pi over 4, we have the matching ones of root 2 over 2. And for pi over 3, we are looking at the coordinates 1/2 root 3 over 2. All right, so for this first example, it says to find the sine of 2 pi. And you actually probably should just pause the video for a minute and try the 10 questions here and then turn it back on and check it. All right, so for the sine of 2 pi, thinking of our unit circle, 2 pi is 1 full rotation back around, so we're back to 0. And the sine at 0 is 0. For the cosine of 3/2 pi, that would be at 270 degrees, and cosine there would be 0. For pi over 6, we are looking at the tangent. Tangent is sine over cosine, or y over x. So looking at our coordinates for pi over 6, that would be 1/2 over the square root of 3 over 2. The 2's drop out, we get 1 over root 3, and if we rationalize it, we would get root 3 over 3. For the cotangent of 7 pi over 4, now that is in quadrant 4, but it still uses the same reference angle here of pi over 4. So picturing going to 7 pi over 4, the only difference with our coordinates is that our y coordinate would be negative. So we have root 2 over 2 and negative root 2 over 2. And when we take cosine divided by sine, or x divided by y for cotangent, we are going to get a negative 1. At 5 pi over 6, we are over here with a reference angle of 1 pi over 6. So again, we're thinking of our pi over 6 coordinates, root 3 over 2, 1/2. The only difference in that quadrant is that root 3 over 2 would be negative. We are looking for the secant, which is the reciprocal of cosine. So we need the negative root 3 over 2 to take its reciprocal. We get negative 2 over root 3, and if we were to rationalize that, we would have negative 2 root 3 over 3. For question 6, we are looking for the cosecant of 5 pi over 3. Picturing in our head the unit circle, 5/3 would be over here, with this being 1/3 as a reference angle. And we are looking for cosecant, which is the reciprocal of sine. So using our pi over 3, the coordinates here would be 1/2 negative root 3 over 2. And we want the reciprocal of our y coordinate. So again, we're going to have negative 2 over root 3, rationalized the same as our last one, negative 2 root 3 over 3. For number 7, we are looking for the cotangent of 4 pi over 3. 4/3 would be all the way to here plus an extra third. So again, we are looking at a pi over 3 ordered pair there. The difference is that now we need x to be negative. So negative 1/2 positive root negative 1/2 negative root 3 over 2. And we want the cotangent, which would be x over y. So we need negative 1/2 divided by negative root 3 over 2. The 2's drop out, our negatives cancel out. We have 1 over root 3 and then rationalized root 3 over 3. For the secant of pi, picturing being over here at pi, coordinates are negative 1, 0. Secant is the reciprocal of our x, or our cosine, so our reciprocal of negative 1 is still negative 1. The sine of 7 pi over 6 would be halfway around our circle plus an extra 1/6. Coordinates for pi over 6, we said were root 3 over 2, 1/2. In this quadrant, though, both of those are negative, and we want the sine, so our answer would be the negative 1/2. And our last one, 2 pi over 3, puts us over here with a reference angle of pi over 3. Coordinates for pi over 3, 1/2 root 3 over 2. In our second quadrant, our x is negative, our y is positive. We want the cosine, which would be the negative 1/2. All right, so moving on, we are looking at our fundamental identities. It says the symbol equals means several different things. It can be the equality of numbers, where we have statement like 1 plus 1 equals 2. We're just showing that two sides are equivalent. It is a true statement. It can be used to represent equivalent expressions, where we have an expression, for example, 2 times x minus 3. Distributing that, we would get 2x minus 6. So again, it's a true statement. It can be used in something called an open sentence, where we have an example here, x squared plus 3 equals 7. This can be true or false depending on what x is. And it can be used in an identity, where we have a statement cosine of t squared plus sine of t squared equals 1. We've talked about that one back in chapter 4. Sine squared plus cosine squared is 1. An identity would be equations that equate two expressions that are true for all values in the domain of both expressions. Now, that statement is important. It has to be in the domain of both expressions. We call that the domain of validity. We have values of the variable for which both sides of the identity equation are defined. So we're going to do a little exploration here of these reciprocal and quotient identities that we learned back in chapter 4. If you look at the questions in the exploration, it says theta being 0 is in the domain of validity of exactly 3 of those basic identities. For exactly 2 of the basic identities, one side of the equation is defined at theta being 0, but the other's not. And then the third one says for exactly 3 of the basic identities, both sides of the equation are undefined at theta being 0. So what we're going to do is take these identities, and we're going to move to another page here so we have some space, and we're going to look at what happens if we take theta and use 0 to replace it. All right, so we're looking at sines, cosines, etc. of 0. Okay, so find a blank page or some scratch paper. We are going to take each of those identities and analyze them again for theta being 0. All right, so our first one said the cosecant of theta is 1 over the sine of theta. All right, that's one of our reciprocal identities. Well, if we look at 0, coordinates are 1, 0, and cosecant is the reciprocal of sine. So cosecant, if our sine is 0, cosecant would be undefined. We cannot take the reciprocal of 0. On the other side, we have 1 over the sine of 0, and the sine of 0 is 0, which makes this undefined as well. So this is a case where we have both sides being undefined. All right, looking at our next one. We have the secant of theta being 1 over the cosine of theta. Well, cosine of theta is 1, So on the right-hand side, we just get a 1. Secant of theta would be the reciprocal of 1, and that is 1 where both sides are defined. All right, our third one, we have the cotangent of theta is 1 over tangent of theta. Okay, so theta again is 0. The cotangent of 0, cotangent is x over y, which means this would be 1 over 0, and that is undefined. On the other side, we have 1 over the tangent of 0, which would be our y-coordinate divided by our x-coordinate, 0 over 1. 0 divided by 1 is fine, but we can't take 1 divided by that. So this is undefined as well, which means both undefined. All right. Our next one says the sine of theta is the reciprocal of the cosecant. Okay. Again, thinking of our ordered pair being 1, 0. The sine is 0. The cosecant would be the reciprocal of 0, and that is undefined. So on one side it works, on the other it doesn't. So this is one where one side works, or one side is defined, but the other is not. All right, our next one, we have cosine of theta being 1 over secant. Cosine for our ordered pair would be the 1. Secant would be the reciprocal of 1, which is also 1. Here again, we have a statement where it works on both sides. All right. Our next identity says the tangent of theta is 1 over the cotangent of theta. Tangent of 0 in this case, tangent is y over x, 0 divided by 1, which is fine, it's 0. On the other side, we have the cotangent. Cotangent is x over y, and that is undefined. So here we have one side working and the other is not. All right, we have two more. Our reciprocal ones, we've got our quotient ones, we have the tangent of theta is the sine of theta divided by the cosine of theta. Again, thinking of our ordered pair at 0. The tangent of 0 is y over x, which is 0. So that side's fine. On the other side, we have the sine of 0, which is 0, divided by the cosine, which is 1. All right, so here's one where both sides are defined. And our last quotient identity says the cotangent of theta is cosine over sine. So cotangent would be x divided by y, so 1 divided by 0, which is undefined. On the other side, we have the cosine, again, 1 divided by 0, undefined. All right, so if you look back, we have some of our identities being defined on both sides. We have some where it is defined just on one, and we have some where it is undefined on both. So let's go back and answer our questions here. Which three have 0 being in the domain of validity, meaning it works on both sides? So the identities where it worked on both sides, we had the secant of theta being 1 over cosine. We had cosine of theta being 1 over secant. And we had the tangent of theta being sine over cosine. So 0 is in the domain of validity. Anytime that you're dealing with a cosine being on the bottom, Again, for that 0, for theta being 0, as long as cosine is on the bottom, or secant, reciprocal, it is defined on both sides because cosine is 1 there. The problem comes when we have sine on the bottom. So for part 2, it says, for exactly 2 of the basic identities, one side works and one is not. The 2 that we had for that, the sine of theta equals 1 over cosecant, and tangent of theta being 1 over cotangent. And then the third one says, which 3 have both sides being undefined? And again, that's where we end up with sine expressions being in a denominator. So cosecant of theta being 1 over sine. Since the sine at 0 is 0, we run into trouble there. We have cotangent being 1 over tangent. And we have cotangent being cosine over sine. Okay, so just making sure that if you are evaluating using these identities for the angle in question, it has to be within the domain of validity. So it has to make the statement defined on both sides. All right, so the next set of identities that we're going to look at is the Pythagorean identities. We have cosine squared theta plus sine squared theta equals 1. That is one that we talked about in our last chapter. Hopefully you remember that one. And that would be a good one to memorize. We do have 3 versions here, but as long as you memorize that first one, you can actually convert it into the other 2 if you need to. All right, so to find the other 2 based on the cosine squared plus sine squared equaling 1, one option is to divide both sides by cosine squared. So if we take each term and divide by cosine squared, all right, we have cosine squared divided by cosine squared, which is 1. We have sine squared divided by cosine squared. That is equivalent to tangent squared. And then we have 1 over cosine squared, and the reciprocal of cosine is secant. Now, notice that I put the square in 2 different spots. Sometimes you'll see it on the outside, sometimes you'll see it here. In both cases, it means that you are taking the trig function of t and you're squaring that answer. We are not squaring the angle. We're not squaring t, we're squaring the sine, cosine, tangent, the trig function of the angle. All right, typically we will write it like this, just as our shorthand notation. So notice that we started with our initial Pythagorean identity and we converted it into this one. Okay, well, if we start with the initial one again, but this time if we divide every term by sine squared, look what happens. All right, so the first term we have cosine squared divided by sine squared. That's cotangent squared. Sine squared divided by sine squared is just 1. And on the right-hand side, 1 over sine squared is the same as cosecant squared. So again, we get cotangent squared plus 1 equals cosecant squared. All right, which is that third one. So again, memorizing the first one allows you to create the other ones if you forget them. Another way to remember it, the second 2 have 1 plus a trig function squared equaling another trig function squared. And the co-words go together. So we have cotangent matching with cosecant. All right, so first example here. It says, find the sine of theta and the cosine of theta if we know the tangent of theta equals 5. And we are told that the cosine of theta is greater than 0, which means it's positive. All right, so we can use one of our identities, one of those Pythagorean identities. We know tangent, so let's use the one involving tangent. We have 1 plus tangent squared theta equals secant squared theta. And we can substitute 5 in for tangent, so we have 1 plus 5 squared equals secant squared. Simplifying on the left here, we get 26 equals secant squared theta, which means the square root of 26 is the secant of theta. And they asked us to find cosine, which is just the reciprocal of that. So the cosine of theta would simply be 1 over the square root of 26. Typically, when we square root, we have to consider the positive and negative, but they did tell us that cosine was positive, so we are just going to use the positive version. Now, in terms of finding the sine, we found cosine, but to find sine, we have a couple options. We can go back to sine squared plus cosine squared equals 1 and use that. Or we could use the tangent. Since we know a tangent and we know a cosine, we could work backwards and find sine. So either one will work. I'll show you both. If we use the tangent of theta equaling sine over cosine, tangent is 5. We don't know the sine, but we found the cosine to be 1 over the square root of 26. We can multiply that 1 over root 26 to the other side, and we end up with the sine being 5 over the square root of 26. Okay? If we chose to use the Pythagorean identity instead, we could have started out saying cosine squared plus sine squared equals 1. Cosine was 1 over the square root of 26. We do have to square that. Squaring it just gives me the fraction 1/26. If we subtract 1/26 from the other side, we have the sine squared of theta being 25/26, and then we can square root. So we end up with the sine of theta being 5 over the square root of 26. So either way gets you the same answer. You obviously don't have to do both of them. One is plenty. All right. We have a few more identities to talk about. Our first one here deals with cofunction identities. Notice that we have two separate angles that they are referring to. In our picture, we have angle A here and we have angle B. In the top half for angle A, it says the sine of A is y over r, okay? Opposite over hypotenuse. Tangent of A is y over x. Secant of A is r over x. Cosine of A is adjacent over hypotenuse, x over r. Cotangent is adjacent over opposite, x over y. And cosecant is hypotenuse divided by opposite, r over y. Now notice with angle B, what was opposite for angle A now becomes adjacent for angle B. And what was adjacent for angle A becomes opposite for angle B. So you'll see some repeats. For example, cosine of A and sine of B, those are the same. The cosine of A, sine of B have the same ratio. Sine of A and cosine of B have the same ratios. Okay? Tangent of A and cotangent of B, or cotangent A and tangent of B. Okay? On this side, secant of A with cosecant of B, and then cosecant of A with secant of B. We call those cofunctions. All right? They are complementary. Angles A and B both have to add up to 90, so they are complementary angles. So our cofunction identities basically say that the sine of the complement is equal to the cosine of the original. Okay, and we can use that same kind of statement for all of them. The cosine of the complement is equal to the sine of the original. Okay, So we have all of our cofunction identities for our 6 trig functions. The next set is the even and odd identities. We've talked about this a little bit back in chapter 4 in terms of sine and cosine graphs. All right, that's our sine curve. It is odd because it has rotational symmetry or symmetry to the origin. So our sine function is a case of being odd. That means the sine of the opposite of our angle is the opposite of the sine of the original angle. And since sine is odd, cosecant is also odd. With our cosine graph, cosine started high, 0, low, 0, high. And this one was an even function because it looks the same on both sides. All right, so cosine is even. The value for cosine of a positive angle and of the negative angle are the same. So the cosine of negative x and the cosine of x are going to be the same value. Tangent, because it involves sine and cosine, it becomes an odd function. We still have these negatives that we have to incorporate in it. So tangent is also a situation of being odd. All right, so we're going to start looking at some examples where we have to use these identities to do some converting. Our first one says if the cosine of theta is 0.34, find the sine of theta minus pi over 2. Now notice that this here is backwards from what we see here. Normally we have it as pi over 2 minus theta. We now have theta minus pi over 2. So we're going to have to do some rearranging here. All right, so the sine of theta minus pi over 2, we are going to rewrite. We're going to factor a negative out of that and think of it as negative pi over 2 minus theta. Okay, now the negative inside, because it's an odd function, is going to have to get pulled out front. So this becomes negative sine of pi over 2 minus theta. But the sine of pi over 2 minus theta is the same as cosine theta. Sine of pi over 2 minus theta is the same as cosine theta. So this becomes negative cosine theta. And we were told that the cosine of theta is 0.34. So we get an answer of negative 0.34. Part B says, using the identities, simplify the expression to 1 or negative 1. We have the sine of x times the cosecant of negative x. Okay? Well, cosecant is the reciprocal of sine, so we could flip that over. And knowing that the sine is an odd function, the sine of negative x is the same as negative sine of x. And in this case, we can cancel the sine x's, but we do have a negative 1 left. All right, example 3. It says to simplify by factoring and using the identities. We want to simplify it down to a power of a single trig function. So notice there are multiple trig functions in our original statements. We want to simplify this down to just the power of a single one. All right, so for the first one, again, there's a couple different ways we could go about this. One option would be to factor a sine of x out. From that sine cubed, we would have a sine squared left. And from the sine x cosine squared, we take the sine x out, we just have the cosine squared left. And one of our Pythagorean identities says sine squared plus cosine squared is 1. So this becomes the sine of x times 1, or just the sine of x. So we have simplified this original expression down to just a single power of x. A single power of a trig function, sorry. The other option, we could convert cosine squared into something involving just signs, since everything else is in terms of signs. So doing that, we can think of it as sine cubed x plus sine of x times, and if we go back, if we have cosine squared plus sine squared equals 1, then cosine squared is 1 minus sine squared. And we can do that substitution. So 1 minus sine squared of x. Distributing, we have sine cubed of x plus sine of x minus sine cubed of x. And then those sine cubes are going to drop out, and we simply have sine of x. So again, that's another option. You obviously don't have to do both. I'm just trying to show you that there are multiple ways to get to the same answer. All right, for part B, we have the secant minus 1 times the secant minus plus 1. If we were to FOIL that out, we have secant squared of x minus 1. But secant squared, if we go back to our Pythagorean identities, we had secant squared being 1 plus tangent squared. So we can do that replacement. Secant squared is 1 plus tangent squared minus that other 1, which simplifies down to just tangent squared. For our next one, notice we have a lot of different trig functions. We have some thetas and some negative thetas, so we need to do some converting. 1 over cosine, we are going to rewrite as secant, and then we have a minus 1. On our next piece, we have cosine squared plus the secant of negative theta. But secant is an even function, so the secant of negative theta is the same as the secant of theta. And 1 over cosecant squared is the same as sine squared. All right, now simplifying inside our right parentheses. Cosine squared plus sine squared is just 1. So this becomes secant theta minus 1 times secant theta plus 1. And we just did this in part B. It simplifies down to tangent squared. All right, the last one that we're going to look at today says to simplify the expression secant of x plus 1 times secant of x minus 1 divided by sine squared of x. All right, so once again, we just simplified that. We FOILed it out, and we found it to be equal to tangent squared. So I'm going to write this as tangent squared of x divided by sine squared of x. Well, tangent squared could be written as sine squared over cosine squared. And then we're multiplying by 1 over sine squared. That's the same as dividing by sine squared. And if you'll look carefully, you'll notice we have sine squareds that are going to cancel each other out. So we end up with 1 over cosine squared of x, and that would convert into just secant squared. All right, so for today's assignment, we are working on page 410, questions listed here.